All right, good afternoon. Here we are for the first lecture of ENGR 2302 Engineering Dynamics. I am Tanya Larson, and I will be the instructor for this series of lectures. So today we're going to have a very brief lecture, just a quick introduction to dynamics, and we will work through, we'll start our actual material from the text, working through that on Thursday. So, first of all, what is dynamics? That's the question that we need to first answer. What is dynamics? So this is a very brief introduction to what is dynamics. What is dynamics? What is dynamics? All right, so, well, let's compare and contrast to statics. The prerequisite to this course is statics, so to answer this, we might also ask, what is statics? So these are kind of correlated. What is dynamics is correlated with what is statics. And so both of these are the study of objects. Both of these are the study of objects. Both of these are the study, if I can keep from screwing up, are the study of objects and forces and bodies. The study of forces and bodies, you might say. And then they also both share one assumption that is that's really defines them, in my mind, relative to courses that come later. And both of these are defined by the rigid body assumption. By the rigid body assumption. And this, I really feel, is definitional to what it means to study statics and dynamics. This is the rigid body assumption is really what distinguishes statics and dynamics from later courses such as mechanics of materials, dynamics of machinery, structural analysis, whatever course you may be taking. So, what is the rigid body assumption? Let's discuss this. Discuss this briefly. The rigid body assumption. So if I have a rigid body, how does this behave? How does a true rigid body behave? Well, a rigid body assumption, or a true rigid body, I'm going to assume that materials or objects do not bend, flex, twist, or deform whatsoever. Do not bend, flex, twist, or deform whatsoever. So in other words, if you are familiar with some topics from mechanics of materials, the kind of material property that I would be assuming, I would basically assume that they have a modulus of elasticity of infinity. Modulus elasticity pertains directly to the stiffness of a material, or we could also say their modulus of rigidity, the G, would also be equal to infinity. In other words, if you're familiar with the topic from mechanics of materials, the modulus elasticity basically describes how much deformation you get for a certain level of loading. So here the equation would be something like E equals sigma over epsilon, where sigma is the stress in the material and epsilon is the strain. And you don't need to worry about this. This is something that you'll see in a later course, but this is something you'll see when you get to mechanics of materials if you haven't taken it already. Do not worry about not knowing what these symbols are. That's fine. This is something from later courses. But the basic idea is that you're dealing with materials of infinite stiffness. You can apply a load. If I have an object here, say a simple prismatic cylinder or prismatic shape, something like that, or a simple cylinder, if I have a rigid body, if I have a true rigid body, if I apply a force P to both ends of this, I can make P arbitrarily large and the deformation here will be 0. So this is the length, and even after applying a load, L final equals L initial, or delta L is equal to 0. There is not going to be any change in length or any change in dimensions. I can apply a load of 10 quadrillion tons to an object and it will not deform at all. So, is this a bad assumption? Is this realistic? I mean, is this realistic? No, it's not realistic, but so does that mean it's bad? Does that mean I'm teaching you nonsense? Does that mean we're going to spend the entire semester just wasting your time? No, exactly. It is not useless. It is useful for understanding the basics. The rigid body assumption is not perfect, but for many applications, it's perfectly valid. Rigid body assumption is not perfect. Assumption is not perfect. Is not perfect, but it is a very useful model for predicting the behavior of objects. Very useful model for predicting the behavior of objects. For predicting the behavior of objects. Now, yes, this is impossible. But there are many things that we will assume as we work through math and engineering and science, etc., that while they may be simplifications, are still perfectly valid. So, for example, if you have studied physics, you may know that what's wrong with the equations of Newton? What is wrong with the equations of Newton, for example? Well, what I'm really getting at here is, if you studied any special relativity, for example, you will know that the equations of Newton, basically all of them, are approximations of the equations of Einstein, right? These are approximations. Now, generally, though, the difference between the equations of Newton and the equations of Einstein are so close together, are so similar, they only differ by a tiny, tiny 0.0000001%. The only exception, the only time you ever need to start worrying about relativistic equations is if you're dealing with very high velocity at some significant fraction of the speed of light, or if you're talking general relativity, you're talking about things near very strong gravitational fields, or in the case of GPS satellites where you need incredibly high precision just for the sake of keeping your clocks aligned, et cetera, et cetera. But we don't need to worry about that. So even the basic equations of Newton that we are going to use through this course, that we used in statics, that we will use in mechanics, materials, fluid mechanics, even those equations are approximations of higher order equations. So everything we do in engineering, everything we do in science is based upon breaking the world down into simpler models, breaking the world down into usable pieces, manageable chunks. Otherwise, we could never accomplish anything. Engineering, as I'll say in this course and other future courses, engineering is all about simplifying. It's all about constructing models. It is all about analyzing the world in a way that can be broken down and simplified. So if you really wanted to, say, consider a very simple object, if I want to talk more about models, consider a very simple object. Just a block resting on a flat surface. Now, if I were to use a statics approach, or say a high school elementary physics approach or something like that, I could simply say that on this block there are two forces. There is weight pulling down and the normal force pushing up. And if it were on an incline, we could model the frictional force holding it up and the force of gravity with components, etc., etc. But that is a simple model. So I am treating the object as a rigid body. I am saying I am treating it as one lump of material. But in reality, if I really wanted to go down the rabbit hole, I could just go deeper and deeper and deeper. First, I could say it's not actually going to be a rigid body. It's going to deform a bit. So when I place this block on the surface, it's going to deform a bit. The block will. And in addition, the surface that it's lying on will also deform. So it's actually, the bottom surface of it is actually kind of going like that a bit, and the top surface will go like this a bit, won't it? If I really wanted to model things very accurately, so if I was doing something like foundation design, I would need to consider something like that. But if I really wanted to go down the rabbit hole, I could go deeper. I could start saying, okay, well, I assume this was linear. Maybe I assumed that it was behaving linearly, but I could do a more exact analysis assuming plastic behavior. Maybe I could divide the block up into maybe I could use a computer program that would analyze the block as thousands of grid chunks called finite element analysis. I could analyze the block as dozens or thousands or millions of individual pieces and analyze the behavior of the block by looking at how those tiny individual pieces behave. And that's kind of how most computer engineering models actually work. They don't consider a building or a machine as one piece. They break it up into a series of chunks and can perform simpler calculations on it. Or I could go deeper. I could say, you know what? Let's go all the way. Let's go to atoms. I'm going to consider every single atom as its own discrete particle. I'm going to need a computer that is more powerful than all the computers on Earth put together, working from now until the end of time. And I'm going to model the behavior of this block by literally considering every single atom in there. I can still go deeper. I can say, I am going to go to subatomic particles. I can look at protons, neutrons, and electrons, and look at the electron clouds and how they're interacting, and doing a giant computer simulation of every single atom and molecule in that thing at the proton and electron and neutron level. I can go deeper. I can start looking at the subatomic level. I can start looking at quarks and all of the full standard model of physics and everything else. Well, I can't do that. I'm not good enough at physics to do that, but I know it's possible. Well, actually, I know it's not possible. You can't have a computer that powerful, not in our lifetimes anyway. Well, maybe, but we'll see. At least nowadays, until someone invents a great quantum computer or something, that's not possible. So it never ends. The point being that we can always go deeper and deeper and deeper. There's always another level of reality to reveal. There's always another assumption that we can peel away that will make our analysis 100 times more difficult. But for almost everything you're going to do, even looking at things at a single atom level is just so far over the top that you would be absolutely insane to even try. There's no reason to do that. The only time people usually simulate individual molecules is if they're trying to say, oh, predict the behavior of a certain molecule. Like maybe you can, a chemist might have a model of a molecule, and maybe they're trying to predict, I don't know, the boiling point of a molecule that they're thinking about creating, or something like that. But anyway, the point being, engineering is all about models. And so even though this rigid body assumption is completely impossible, it is still perfectly useful and valid for certain applications. All right, so let's see where statics and dynamics differ. So let's talk about the differences. Differences. Statics versus dynamics. Well, really it all comes down to one equation. And that is Newton's second law. The equation that I consider at the heart of statics and dynamics is Newton's second law. The sum of forces is equal to mass times acceleration. Now, in statics, we let that acceleration be zero. And that really is the defining characteristic of statics. So in statics, we say that the acceleration is zero, and therefore we'll just say the sum of forces is equal to zero. And that does greatly simplify things, but because of that, we can spend more time focusing on this. We look more at the sum of forces than the motion of things. We'll spend a lot of our time focusing on this. We'll look in detail how forces distribute within bodies. How forces flow in bodies, in objects or structures, etc. So, for example, you look at things like trusses, you look at things like frames, you look at things like, even things like fluid statics, where you look at the forces of pressure in a body of fluid, that kind of thing. And you also spend time working on moment of inertia, etc. So because things aren't moving, you have the luxury of looking at things in greater detail. When the moment we start things into motion, the moment we get to dynamics, we will not be able to look at objects in quite so much depth. In dynamics, the A is not equal to zero. So then we will say the sum of forces is equal to mass times acceleration, where A is not equal to zero. And so we're going to spend more time focusing on this side of the equation. We're going to say we will look in detail at how moving bodies behave. So let me show some applications of this, or some specifics of this. So statics versus dynamics, again, let me list this here, statics versus dynamics. Statics and dynamics, if I can spell dynamics properly. Here, statics and dynamics. Let's look at some things that you will only see. What are some unique things? Topics. Unique topics for each of these. Each of these, because they are allowed to, again, back here, when statics, we are looking very deeply at the sum of forces side of this equation. When we are at dynamics, we're looking very deeply at the acceleration side of the equation, the motion side. And because of this, I will not say statics or dynamics one is superior to the other. It's not. It's not simply a matter that dynamics is just statics plus motion. That is very much a simplification. There are things we looked at in statics that we will never look at in dynamics. Because things weren't moving, we were allowed to look at things, certain topics, in much greater detail than we would be able to if we're looking at dynamics. So, for example, in statics, we were able to look at things like trusses and frames. We were able to look at trusses and frames, and especially trusses. Think about that. We were able to perform analyses of trusses using things like the method of sections and the method of joints, etc. And we were able to get really into the nitty-gritty of the internal forces in members. And I could give you a problem with a very large truss, and I could give you a problem with a truss made of 20 pieces, and it would be perfectly reasonable to ask you to find all the forces in those members. And that's really not that difficult. So and the reason we were able to do that was, again, because things weren't moving. If I set that truss into motion, suddenly that's not possible anymore. I can't realistically ask you in a dynamics problem to model the behavior of a moving truss. And at first you might think, well, why would a truss move? Well, in reality, trusses and bridges do move. That their deformation ideally isn't very large, but even large things do move. And you often need to use computer programs to really model their motion. Or if you want to really see how structures move, you may take a class in structural dynamics, which often is taught at the graduate level or the senior level for civil engineers. Other things that you only look, another thing we only look at in statics is things like fluid pressure. When you take a fluid mechanics class, you will learn how the dynamics of fluid operates. But for this topic here, for our course here, we'll only be looking at, for this set of courses, we only consider fluids as at rest. Oh, and we also then look at things like shear and bending moment diagrams, internal forces, and bending moment diagrams. Bending moment diagrams. And some other topics as well. But these are the most obvious ones. I will not ask you to draw a shear and bending animation. I mean, that would be slightly cruel. Yeah, just to draw, imagine, oh my God, that would be evil. No, I would not do that. We do not have time for that either in class or during a lecture. But conceivably, you could actually derive equations for how shear and bending moment diagrams will change versus time. There's no reason you couldn't do that. But we'll not be doing that in this class just because, again, statics, because things aren't moving, you can afford to look at the nitty-gritty, look at the forces inside members very carefully. But again, then, so in dynamics, we can look at things like, well, obviously, things in motion. That's the most obvious thing. Things in motion. Oh, you can look at, what else? You can look at things rotating, rotational systems. You can use more energy methods, which we didn't really use very often in statics. energy methods will be very useful. You can use systems of several components as long as that number of components is small. Of a few components, each in motion. Etc. And we will also, towards the end of the semester, get into vibration. Things like damped and undamped vibration, that kind of thing. So in general, we are looking at how objects move, how they rotate, how they translate, how they fly through the air, how they rotate, how the interplay of energy and momentum, essentially. Basically, this is the interplay. By the end of the class, we should be fairly good at looking at the interplay of energy, force, and momentum. In statics, momentum never even appears. And the reason for that, of course, is that we are usually considering objects that are at rest. Now, the equations of statics actually do work perfectly well. Even if things are moving at a constant velocity. But things can't be in motion, but they have to be in a constant velocity. But when in dynamics, we'll consider systems that are actually changing in direction, they're changing in velocity, etc., etc. So this is just a brief introductory video on some of the topics of dynamics, and we'll look at this in more detail in the first real lecture on Thursday. So if you have any questions, feel free to see me during office hours or send me an email, and we'll see each other again on Thursday. And as always, thank you.